Okay, hi everyone. So this is going to be a video lesson about systems of linear equations. So we are getting started in linear algebra. By the time you see this, you've probably already gotten an introduction from me about the class and about the syllabus, so I'm not going to go over all of that again. But basically, the way this is going to work is at the beginning of each video, I'll try to do a quick intro like this, tell you what we're going to be talking about, and then I'll switch over to my document camera, which you can't see, it's right out of the field of view here. But I'll switch over to my document camera and start writing, and mostly you'll be seeing my hand and not my face. And, hopefully it looks like I'm writing on a whiteboard. Hopefully it's easy to read. And yeah, that's what we'll do for most of the video. I'll tell you that this first section of the course is covering some things that you might have seen in an algebra class at some point. We sometimes cover this in college algebra or pre-calculus. Some classes cover it, some classes don't. So this is basically just to make sure that we're all on the same page. Because even if you've seen this topic before in an algebra class, it's probably been a while, so it's good to get a refresher. And if you haven't seen it until now, that's okay too. So we'll get everybody on the same page, and later sections are going to do some more advanced things with this. So it's good to make sure that we are comfortable with systems of equations. All right, so let's go ahead and get started. So, systems of linear equations are basically a perfect place for us to start this course because we're going to be talking about them the entire semester. Let's start off with a definition. But it's not going to be a definition of linear systems yet. It's just going to be linear equations. So we're going to say a linear equation is one that can be written in the form and we want to write kind of a general form here. We're going to say a1 x1 plus a2 x2 plus, the idea is that the x's are variables or the x's are unknowns and the a's are like coefficients in front of them. And if we're being general, we don't really know how long this goes on. There could be an a3x3, a4x4. And since we don't know how long this goes on, we're just going to say ... It goes up to an xn, and there's a right-hand side. So underneath this, let me just say what some of these things mean. We're going to say x1, x2, ... up to xn are variables. A1, A2, ... up to an are coefficients. So we could think of those as constants. Also, b is a constant, not a variable. And what other letter is here? N. N is a positive integer. So maybe n is something like 10, and that is going to be our definition of a linear equation. So we're not talking about systems yet, but we'll get to that soon. So first of all, I just want to give some quick examples of linear equations because we've seen them, and let's see a few more, and let's remind ourselves what they look like. So for example, 3x1 minus x2 equals 6. That is a linear equation. We're not going to worry about solving it right now or anything like that. I just want to give a few examples. It's an equation that can be written in this form. And the idea is that the coefficients could be positive or negative. Even though we wrote a plus sign up above, a2 could be -1. So we can have a subtraction show up. So that's a linear equation. Another example would be x2 equals -x1 plus 4. Now you might look at this one. This is a second example of a linear equation. You might say this doesn't really look like it's in that form. Well, that's true, but remember, the definition just says it's an equation that can be written in this form. It doesn't mean that it has to be written in this form. What I mean is, we could take this and rearrange it or rewrite as, like if you move the x1 over to the other side. Doesn't it look like this? You just add x1 to both sides. And now it looks like the standard form. It was a linear equation all along, even though it might not have looked like it at first. I'll show you one more example of a linear equation. 2/3 x1 plus square root of 2 times x2 minus 0.2 x4 equals 0. This is a linear equation I chose to write in this way as an example, just to demonstrate a few things. So first of all, notice that the coefficients don't have to be integers. We never said they have to be integers, so the coefficients can be things like fractions, square root of 2, could be a decimal, they could be positive or negative. And in this case, notice that the variable x3 doesn't appear. There's no x3. One way to think of that is you could just say that maybe the coefficient in front of it was a 0. So it's like we have 0 copies of x3. So linear equations can look like lots of different things. They're not always going to be integers. I will say off to the side here maybe that linear equations do not have terms such as x squared, square root of x, or x1 times x2. Okay, so you could still have an equation that has those sorts of things in it, but it would not be a linear equation. These would be nonlinear. And even though those sorts of situations can get really interesting, that's not really the topic. This course is linear algebra, so we are focused mostly on linear equations. All right, so we defined linear equation, we saw a few examples, and we've got a little more terminology. I mean, it's the first section, so we need to know what we're talking about here. Terminology. First of all, a system. I'm going to underline that. A system of linear equations. Or linear system. Is a group of linear equations satisfied simultaneously. And that word simultaneously is important, that you have a group of multiple equations and they are all satisfied at the same time. I guess by some value of x1 and x2 and x3 and however many x's there are. Something that makes all of the equations true at the same time. Which brings us to a solution. A solution to a system is an ordered list. For now, we're going to write it as S1, S2, ... up to Sn. That makes all of the equations true when S1 through Sn are substituted for x1 through xn. All right, so I'm at the bottom of my page here, so I'm going to be moving this in just a moment. I'll give you a moment to see that. So the idea is that in algebra classes that you've had before, a lot of times you have an equation, you want to solve for x. This time there's more than one x. There's more than one unknown. So it's not good enough to just solve for x. We need to solve for x1, x2, x3, however many there are. And that means that the solution is actually a list of numbers. N of them, in fact. All right, so we'll move this up. I'll be trying to move this up and leave it kind of visible if I can. It's kind of hard to fit everything on my desk here. Okay, so next piece of terminology is the solution set. Let's underline that. The solution set of a system. This is simple. Is the set of all solutions. How about that? The solution set is the set of all solutions, because we didn't say that there has to just be one solution. Maybe there's more than one. We'll be talking about that soon. Maybe there's one solution. Maybe there's more. Maybe there's none. Maybe there's a problem where there's no solutions. We'll see. And two systems are equivalent if they have the same solution set. One other thing that I think I'll just say out loud, I don't think I'm going to write it, is just when we use the word solving, if we say we are going to solve a system, solving means finding all solutions. If I say solve the following system, it means find all solutions. Or another way to think of it is it means find the solution set. So let's start by talking about small systems. Okay, I said earlier that n, the number of unknowns, could be any positive integer. We could have 10 unknowns. We could have 100 unknowns. But let's start by talking about systems in two variables. Let's just start with two. Systems in two variables are easy for us to visualize and easy for us to understand. And in this case, it's often x and y instead of x1 and x2. You know, if there's only two variables, a lot of times we like to call them x and y. And systems, linear systems in two variables represent lines in the xy plane. I'll show you an example. Maybe we'll even talk about solving this one. All right, example, system. 3x minus y equals 6. X plus y equals 4. This is a group of equations that I would like to have satisfied simultaneously. And in order to group them together as a system, we often put a little squiggly bracket to the left of them. That indicates that they are grouped together as a system. So we often write the bracket. And what I'd like to show you is that there is an equivalent system just by sort of rearranging it, we could say y equals 3x minus 6, y equals minus x plus 4. And I hope you'll take a look at these two systems and see that they are essentially the same equations. They've just been rearranged. So they should have the same solution set. The thing that's nice about the first way that I wrote it is the first way is kind of our standard way of writing linear equations from the definition of linear equation. The nice thing about the second way I wrote it is this is y equals mx plus b. We can see what the slope is. We can see what the y-intercept is. So if we're going to visualize these in the xy plane, maybe we'd say the second form is convenient. So let's draw a picture here. And we should all be able to draw lines. You know, if you're given an equation of a line, you should be able to draw it. So xy plane. Let's see, what kind of scale do we need? Well, the y-intercepts are -6 and 4, so I need to make sure that I go down to at least -6. All right, there's -6. And I'll just try to use that same kind of scale vertically and horizontally. See, there's the 4. Okay, that's pretty good. All right, let's draw these lines. So the first line, y equals 3x minus 6, has a y-intercept of -6 and a slope of 3. Slope of 3 means for every 1 unit we go over, we go 3 units up. So it goes up to here, goes up to here, here. Okay, should look like that. That's y equals 3x minus 6. And the other line, the y equals -x plus 4, has a y-intercept of 4 and a slope of -1. So for every 1 unit we go over, we go 1 unit down, because the slope was -1. Okay, should look like that. Y equals -x plus 4. So what is happening here is these two lines, they intersect somewhere, right? There is a point in the xy plane that seems like it is on both of these lines. And I'm going to kind of indicate it here. I'll just kind of draw a dot and say, where is this point? I guess if I were to try to estimate this based on the graph, it looks like 2 point something, comma 1 point something. Let's just say question mark, comma question mark. Maybe if I look closely, I'd say it's like maybe 2.5, comma 1.4 would be my guess. But we don't need to just guess. We can work on finding this, and the way we find this is by solving the system. So there are many ways to solve a system of linear equations. And part of what we're going to be doing over the next couple of lessons is learning different ways to solve them. But for now, one simple way to solve the system is to say if y equals this and y equals that, these right-hand sides must be equal to each other. If they're both equal to y, they must both be equal to each other. So I took right-hand side equals right-hand side. This is one way to solve. I like this because I could add x to both sides, get a 4x, add a 6 to both sides, get a 10. And I get x equals 2.5. Generally, when you're solving a system, if you find the value of one variable, it makes it easier to find the value of the other ones. So what is y? Well, y is 3x minus 6, right? You could use the other equation if you wanted, but let's just use 3x minus 6. So 3 times 2.5 minus 6. Give me 7.5 minus 6, or 1.5. So a minute ago, I looked at the picture and said that this point looked like maybe 2.5, comma 1.4-ish. So not too far off. We're going to say that the point of intersection is 2.5, comma 1.5. We found that algebraically, and it also agrees with what we see graphically. And I will say that this is the only solution to the system. It's the only place where those two lines intersect. Now, how do we know that? We could kind of say from the picture, it looks like the lines aren't going to intersect anywhere else. We could also say from the algebra that we did, if there were any other solutions, the algebra would have given them to us. But it kind of does raise a broader question for discussion. You know, is there always one solution? So I'm going to say, given a linear system of two equations in two variables, how many solutions can there be? And if I was asking you this in person, maybe I'd give you a minute to think about it. Of course, you could always pause the video and think about it. I'm going to tell you that there are a few different cases that we could find ourselves in. It's going to be 3 cases. Let's leave a little bit of room for each one. Let's have a case 1, case 2, and case 3. 3 possible outcomes for a system of this size. So case 1 is going to be kind of like the example that we had above. I'll draw like a quick sketch of 2 lines that maybe resemble the problem we did above. So you have a line and another line, and they intersect somewhere, and there's one solution. And these lines are not necessarily perpendicular. I mean, they could be perpendicular, but they don't have to be. In this case, they were not. All right, so it kind of feels like if you were to pick 2 random lines, can you imagine like picking 2 random lines in the XY plane? It seems like they would probably intersect somewhere at one point. However, there is another possibility, and that is you could have a line that goes like this and a line that goes like this. And if these are drawn just right, you could have 2 lines that never intersect each other. And if they never intersect each other, we say that there are no solutions. And this happens when we have parallel lines. So in fact, if this was written as a system of linear equations and we were trying to solve, we would find no solutions, because we could find no points of intersection. So we have another name for this that I'll write underneath it. We say the system is inconsistent. It's an inconsistent system. It has no solutions. It's still a linear system, though. And then case 3 the final case here is if you have your xy plane, you could have a line that goes something like this. And then you could have the second line could go something like this. What I'm trying to do here is I'm trying to show two lines that overlap exactly. Two lines that overlap each other exactly. If that happens, well, what are the points of intersection? I mean, they intersect here and here and here and here. How many points are on this line? There's infinitely many places where these lines are touching each other. And we say that there are infinitely many solutions. So the solution set would be a set that contains infinitely many elements. So these lines overlap exactly, or you could just think of them as being the same line twice. You could say, well, these two equations are really just the same exact line given to us twice. And those are the only three cases. Those are the only three answers to this type of question if there are two equations and two variables. So this means you get one solution, no solutions, or infinitely many. You'll never get a linear system of this size that has like exactly two solutions. It just can't happen. You can't have a system of this size that has exactly three solutions. If there's two or three, no, there has to be infinitely many, or just one, or none. The only way you could really get the lines to intersect in like two places would be if one of them was a curved line. And if that were the case, then you wouldn't be talking about linear equations. Okay, so that's good for small systems, but in fact, I'm going to tell you that in general, these three cases are the only possibilities for any linear system. Meaning not just two equations, two variables. Now that's kind of a bigger statement. This is something that maybe we could state as a theorem, try to prove it. We're not going to do that right now, but we will be proving other things this semester. But yeah, if you had more equations, more variables, you're still going to always have one solution, no solutions, or infinitely many solutions if we're talking about linear equations. By the way, if there are three variables, then the linear equations represent planes in three-dimensional space. And at some point we might draw those. I don't know if we're doing that today. If you have four variables, well, in that case, I guess you're thinking of some kind of flat four-dimensional objects in four-dimensional space, and at that point it becomes really hard to visualize. But we don't really have to draw these pictures. If you think of that one example we solved a few minutes ago, we drew a picture of the two lines, but we didn't really have to draw that picture. We got the solutions by using algebra. The solution by using algebra. So we don't need to draw a lot of pictures in this course. Occasionally, it's good to draw pictures for some understanding, but the algebra is really what gets us the answers. So, next, our big goal is going to be to discuss how to solve systems, and there's a few ways to do that. First of all, we're going to start by talking about how to solve systems that are in a nice form. So let's talk about systems in triangular form. I'll show you an example of one. I think to explain what triangular form is really best just shown by example. So here's a linear equation. Here's another linear equation. And here's another linear equation that's a really small one. So this is a system. If I put the little brackets next to it to indicate that we're considering these equations together. So the reason why this is called triangular form is because the left-hand sides, I'm going to try to use a blue pen here to show this. The left-hand sides make this nice triangle. See that? And they only really make that triangle because I wrote these equations in a nice orderly way. I kind of put the x2 above the x2, I put the x3 above the x3s, I put the equal signs all kind of lined up on top of each other. The right-hand sides are all lined up on top of each other. We like to do that in this class, to keep things nice and orderly. And when you do that, sometimes you'll see this triangle shape. And we start with these because systems in this form can be solved by substitution. Remember, what does solving even mean in this case? We've got 3 equations, 3 unknowns. Solving means we want to find x1, x2, and x3. Well, I'm looking at these 3 equations, and it seems like x3 is kind of given to us. x3 equals 2. That's the 3rd equation. It's giving me x3 for free. So let's start by saying equation 3 tells us that x3 equals 2. The entire solution is going to be x1, x2, x3. So we have a third of the answer already. Okay, so if we know what x3 is, let's look at the other 2 equations and see which one of them seems more useful. I think the second equation now would be useful because we could just plug in 2. I used the phrase plug in. I guess a more proper term for that is substitute. So I'm going to say in equation 2, I am going to make that substitution. I'm going to put 2 in place of x3. The reason we do that is because now we have one equation with one unknown, move some things around, and this is going to let us solve for x2. x2 turns out to be 3. Well, there's only one equation we haven't used yet, and there's only one of the unknowns that we haven't found yet. So let's move on to equation 1, and let's substitute the values that we know. We know x2 is 3. We know x3 is 2. We get an equation that looks like this. And from this, if we do a little bit of arithmetic, we could find out what x1 is. We're going to subtract 6. We're going to subtract 3. So this thing is going to be 2x1 equals 1. So I get x1 equals 1/2. So we finished it, right? We found all 3. I'm going to move up here, and I'm going to say that we found the solution is... Remember what we said a solution is earlier? It's like S1, S2, ... up to Sn. In this case, it is 1/2, comma 3, comma 2. That's the x1, x2, x3 that we found in that order. x1, x2, x3. If we were somehow thinking of this visually, like if we wanted to try to graph this, well, it would be a 3-dimensional graph, and this would be a point in three-dimensional space. And maybe in that case, you could think of it as x, y, z. Something, comma, something, comma, something. You know, it's an ordered triple. The point of all this is that systems in triangular form are easy to solve. We were able to get the solution pretty fast. So that's great if you get a problem in triangular form. Of course, you know, not all systems will be in that form. I also want to tell you that this strategy is sometimes called back substitution. I'm going to underline back. It's back substitution because we work backwards, in a sense. In a certain sense, it's like we worked backwards. We were from the bottom up. Put that in parentheses as a side note, I guess. So in case you hear me refer to this as back substitution, it's because we used equation 3, the bottom one. Then we used equation 2. Then we used equation 1. So sometimes that's the way to go. So if I gave you a system of this sort of size in triangular form, you could try to do this and find the solution if there is one. Next, we need to talk about systems that are not in triangular form. So I'll show you another example. Let's say we are told to solve, and we're going to be given a system x1 plus 2x2 plus x3 equals 4, 3x1 plus 8x2 plus 7x3 equals 20, 2x1 plus 7x2 plus 9x3 equals 23. I'll just give you a chance to see that. And we'll talk about how to solve this together. All right, so it's not in triangular form, right? So I don't really want to try to use back substitution right away. Here's an idea. Let's try to find an equivalent system in triangular form. Remember what the word equivalent means? We mentioned that earlier. Two systems are called equivalent if they have the same solution set. So what I'm suggesting is maybe we could find an equivalent system so it has the same solution, but in triangular form so that it's easy to solve. We can do this by some combination of, there's a few steps. There's a few steps that we can do, 3 steps, and it's some combination of these 3 steps is going to get this done for us. So first of all, by adding a multiple of one equation to another, second, multiplying an equation by a non-zero constant, and third, by interchanging the positions of equations. So I claim that by some combination of these three steps, when I say some combination, I mean we might not do them in this order. I didn't number them 1, 2, 3 because we might not do them in this order. And we might actually need to do one of these steps more than once, or we might need to do one of these steps not at all. But by some mixture of doing these types of things, we can actually find a triangular system that's equivalent to this problem. I'll show you this, and this is something that we're going to need some practice. It's going to take a while to get the hang of it, but it's a pretty powerful strategy. All right, I'm going to start by rewriting the problem down here because we wrote a bunch of sentences, and let's get the problem again. When I write it, I'm going to try to write it nice and neat with like all the equal signs lined up, and x1s are on top of each other and x2s are on top of each other and so on. I mean, it's definitely more work than a system of two equations with two variables. But we can do this. It's okay. There's the problem again. And I want to do some of these steps. So here's what I'm going to do. I'm going to draw an arrow. And I have an idea for one of these steps. We're not going to be able to get this in triangular form in a single step. This is going to take multiple steps. What I'm thinking is it's this kind of lower left area, like this 3x1, this 2x1, 7x2. Like if those weren't there, then it would be triangular. If that was just empty space over there. And I'm thinking, what do I have to do to get rid of them? Like how could I get rid of that 3x1 or that 2x1 or the 7x2? I'm going to focus in on the 3x1. If I could get rid of it, I think we'd be one step closer to triangular. And there is a way I can get rid of it. I am going to add -3 times equation 1 to equation 2. So I'm using the first step up here, adding a multiple of an equation to another. And I'm adding -3 times equation 1 to equation 2. It's going to give me an equivalent system. Now, the first equation is not changing. So let's just copy it down. In fact, the third equation is not changing, so I'm just going to copy that down also. It's the second equation that's going to be changing because we're adding something to it. -3 times equation 1 is getting added to equation 2. So let's think one term at a time. If I did -3 times x1, it's -3x1 getting added to 3x1. That knocks out the 3x1. That's exactly what I wanted. It's going to cancel that out. We're going to have an empty space here. But as a consequence of doing this, we also have to do it with all the other terms. So -3 times 2x2 is -6x2 getting added to 8x2. -6 plus 8 is 2x2. Next, -3x3 is getting added to 7x3 to give me 4x3. And finally, the right-hand side has to have this done to it also. -3 times 4 is -12. Add that to 20, and you get 8. So I claim that this is one step closer to being triangular because we've got that empty space there. Next, I think I would really like to get rid of this 2x1 in the lower left. If that was empty space, like if there was a 0 there, it'd be even closer to the triangle shape that we're looking for. So again, I'm going to add a multiple of an equation to another. To knock out that 2x1, I'm going to add -2 times equation 1 to equation 3. And right now, when I do this, I'm not changing equation 1, so I'll just copy it. I'm not changing equation 2, so I'll just copy it, so that we make sure we don't lose anything. But equation 3, let's see, that's the whole point of this. -2 times x1 added to 2x1 is 0. So this lower left spot is just a 0. Moving on, -2 times 2x2 is -4x2 getting added to 7x2, so 3x2. And then -2 times x3 is -2x3 getting added to the 9x3 that was already there. Gives me 7x3. -2 times 4 is -8. Add that to 23 to get 15. We're almost there. Now, is this triangular form? No, not quite, because we got that 3x2 in the way, but maybe there's something we could do about that. Before we do anything about the 3x2, there's something about this system that's kind of bugging me. In particular, there's something about the second equation. The second equation has a 2, a 4, and an 8. And I think, you know, when I've got an equation where everything is a multiple of 2, we could just divide everything by 2, right? For that equation, I mean. If you divided everything by 2, it would make this equation simpler. Now, is that one of the things we're allowed to do? It doesn't say anything about dividing. But we're allowed to multiply an equation by a non-zero constant. So what I'm going to do is multiply equation 2 by 1/2. Now, technically, I think you could say that this step is optional, but I think it's going to make equation 2 easier to work with. And we probably could have done it one step earlier. Uh, 15. Okay. I just think that looks easier to work with now. All right, one more step, and we'll be in triangular form. So our one more step is doing something to get rid of this 3x2. Because if that was gone, then this would be that nice triangular shape. Adding a multiple of one equation to another seems like it's been very helpful for us. So that's kind of going to be my first idea. I want to add a multiple of equation 2 to equation 3 to knock this out. How about we add -3 times equation 2 to equation 3. Now I'm only adding something to equation 3, so equation 1 doesn't change, equation 2 doesn't change, and I think that we should copy them down to make sure that we don't lose anything. This is an entire system that we're thinking of as like one object, so we don't want to just lose parts of it, copy it each time. All right, when I do this, let's see. The empty spot plus the empty spot is still 0. -3 times x2 is -3x2 that gets added to 3x2 to give us a 0 here. So we can move on to the next spot. -3 times 2x3 is -6x3. That gets added to the 7x3 that was already there. 7 plus -6 is 1x3. And then -3 times 4 is -12. Add that to 15 and you get 3. We did it. We finally got this in triangular form. I'll write that underneath. It's now in triangular form. Should we draw the triangle? It's optional if you want to do that or not, but I'll go ahead and do it this time. This was what we were trying to get. On the left-hand side, it looks like this. And we were saying earlier that systems in this form can be solved by substitution, or in particular, back substitution. So we're going to be able to finish solving this pretty quickly from now. The hard work is done. By the way, this triangular form we're talking about, you could think of it as a triangle. Another idea, though, is you could think of it as kind of like a staircase. See this? A staircase pattern. Walking down the stairs. Okay. Let's do substitution. So let's write some of this over here. Substitution. Back substitution suggests that you start from the bottom up. So start with equation 3. Equation 3 is perfect because look at this. It gives us x3. That's part of the answer. Let's work our way up and see what happens. Equation 2, substituting as we go. So x2 plus 2 times 3 equals 4. 2 times 3 is 6. This gets me x2 equals negative 2. x2 is negative 2. One more to go, working our way up. So now we're going to use equation 1. And it says x1 plus 2 times negative 2 plus 3 is 4. Let's see whatever this gets us. x1 minus 4 equals 1. So x1 equals 5. Are we done? Should we just like circle this and say that's the answer? Well, I think we should write our solution in that sort of standard form that we had earlier in the definition of solution. And in this case, it would be the x1 we found, the x2 we found, and the x3 we found. So it should go 5, comma, negative 2, comma, 3. And I want to be clear about something that this is one solution, right? We don't call this 3 solutions. We don't call this 3 solutions. It's not like 5 is a solution and negative 2 is, it's not like that. There is one solution and it is the solution 5, comma, negative 2, comma, 3. And you have to write it in that order. Even though we found the 3 first, and then we found the negative 2, and then we found the 5, when you write your final solution, you want to do the x1, x2, x3. As a side note, let's try to remember, what is this all about? This is about finding values of x1, x2, x3. Here, I'm going to kind of just write this underneath. x1, x2, x3. It's about finding values of x1, x2, x3 that if you put them into the original system, all 3 equations will be satisfied simultaneously. All of these equations will be true at the same time. Only with this value, this value, this value. We can kind of check this. I'm going to section this off. We could check this answer. I mean, that's one of the nice things about math classes is sometimes you can check your answer. So I'm looking back at the original problem, not the kind of changed around systems that we did. But let's go all the way back to the beginning and try putting our answer in and see if it works. So it would say 5 plus 2 times negative 2 plus 3 equals 4. And we're checking to see whether or not this works. So I'm going to put a little question mark here. Like, is this true? And we can check pretty quickly. I think 5 minus 4 is 1. There's a 3 here. Yes, this looks good. That checks out. You could check equation 2. That would say 15 minus 16 plus 21. Does this equal 20? 15 minus 16 is -1. -1 plus 21. Yes, this does work. And equation 3. They have to all be true. It's not good enough for just 2 of the equations to work. All 3 of the equations have to work for this to be the actual solution. Does this equal 23? I mean, this right here would be -4. All right, -4 plus 27. I can see that that does equal 23. So this was just little scratch work after we finished the problem. And you don't really have to check your answers, but occasionally I'm going to do it just to remind you that we can. And after all, that is what the solutions mean. That is what they represent. And by the way, remember earlier we said that systems either have one solution, no solutions, or infinitely many. And this has one solution. This is the only solution. We will see some of those other cases pretty soon, but I'll just tell you right now that if there were other solutions, the algebra would have given them to us. And if there were no solutions, the algebra would have shown us that. We found one solution, so that's the case that we're in. All right, let's move this page up and talk about this a little more. So that problem took a while to solve, right? And it's this whole process of, the system was not in triangular form, and we followed some weird sequence of steps to try to get it into triangular form. So note the process of converting a system into triangular form is called Gaussian elimination. That is the process that we did on that problem. So in the previous problem, we solved the linear system by performing Gaussian elimination, and then towards the end, we did back substitution to finish it off. It's called elimination because as we try to get it in triangular form, it's like we're eliminating variables. And it's called Gaussian because it's named after Gauss, even though it was kind of discovered by several people. So we'll be using that phrase a lot. Gaussian elimination, just a powerful process or strategy using a combination of steps in algebra to convert a system to triangular form. Next, we want to talk about systems and matrices. Matrices, well, we haven't used that word yet in this class, but matrices are another big topic of linear algebra. So I'm going to start by saying if we are given a system, all right, let's have an example system to work with. Did I mention yet that systems can represent all sorts of interesting things in real life? Linear systems show up in science, business, economics, engineering. Right now, we're focused on the theoretical side of it, though, so maybe we'll see some of those applications later. All right, we've got a little system to play around with as an example. I'm going to say we can write a matrix based on the system. Here, let's move this up. If you think about the previous problem we did, where every step that we did, I kept copying down equation 1 and equation 2. I was copying down the equations that weren't even changing. And every time we wrote an equation, we had a bunch of plus signs to write and a bunch of equal signs and x1, x2, x3. But really, when you look at a system, it feels like the coefficients are the parts that matter the most. I mean, we know there's going to be equal signs. We know there's going to be x1, x2, x3. So we write a matrix that just sort of has the coefficients, which, you know, if there's no coefficient shown, then I guess the coefficient is 1. We have 1 copy of x1. We have -1 copies of x2. We have 3 copies of x3. We have 1 copy of x1, 2 copies of x2, -2, 3, -1, 5. And I'm also going to write the 4, 10, 14. Those constants are technically not coefficients, but they also seem important to the system. And we write these square brackets around the whole thing. When we do this, we do this with 1 row for each equation, right? We have a row of numbers, another row of numbers, and another row of numbers. And this is known as the augmented matrix of the system. It kind of takes the most important information about the system and strips away all of the other symbols. And you could say that this matrix contains all of the information that we need to work with this system. Off to the side, just in case you haven't seen this in another class, I'm going to mention that a quick definition of matrix. We would say that a matrix is a rectangular array of numbers. Sometimes they're talked about in algebra classes, sometimes they're not. A rectangular array of numbers, and I'm just going to say more about these later. Okay. When you only have one of them, you call it a matrix. And when you have multiple, we use the word matrices. That's the plural form of matrix. Now, if we take a system and then we kind of turn it into the augmented matrix, the key idea is that to solve the system, we can perform Gaussian elimination on the augmented matrix instead of the equations. All right, so we were doing things earlier in that example, like, you know, add a multiple of an equation to another one, or multiply an equation by a non-zero constant. And I'm saying we could do that with this matrix, and then we wouldn't have to write all the other extra symbols, x1, x2, x3, equal signs, plus signs. We can just kind of work with this as like a grid of numbers. And that's really nice to just work with a grid of numbers and then like change it a little, change it a little, change it a little, and get it into triangular form and get the solution out of it. When we do this, we're really working with rows instead of equations. So this is sometimes called row reduction. So we're working with rows where each row represents an equation. You remember a little bit earlier I had the 3 steps that we were allowed to use some combination of. Gaussian elimination essentially was a combination of 3 steps. I don't even think we used all 3. But anyway, we should remind ourselves what these steps are. And in particular, I'm going to now write them in the context of rows of numbers. Instead of thinking of equations, I'm just going to think of rows of numbers. So the allowed steps are, you can add a multiple of one row to another. You can multiply a row by a non-zero constant. And the third one, I think, is the one that we didn't use before. This is that we can interchange rows. So, by the way, when I say interchange rows, I just mean we're going to swap them, like swap row 1 and row 2. If you think about each row represents an equation, the idea of interchanging them is that if you wrote 3 equations and then you wrote them in a different order, it'd still be the same equations. So that's why we're allowed to interchange the rows. And collectively, these are called elementary row operations. So we use a combination of several elementary row operations to perform row reduction, which is really just another way of thinking of Gaussian elimination. This is all to help us solve systems. So I'd like to work through 1 or 2 examples here. And I'm going to start with the system up here. I'm going to actually work through solving it. And I'd really like you to think of it as kind of like what we did before. And it's really just a different way of writing this process. I'm going to write it with matrices, but it is equivalent to what we did before. Okay, this is the system 10, 3x1 minus x2 plus 5x3 equals 14. So first of all, we form the augmented matrix of the system, which I already did above, so I just need to copy it. 1, -1, 3, 4, 1, 2, -2, 10, 3, -1, 5, 14. Okay. By the way, we're about to do some steps. We're about to do some row operations. But by the way, in case you're wondering, what's with that word augmented? Like, why do we say this is the augmented matrix of the system? Why don't we just call it the matrix? In case you're wondering, the word augmented, it's because we're including not just the coefficients, but we're also including the right-hand side. That's what technically makes this augmented. And sometimes in some books, you'll even see people draw a little line or a dashed line. And I'm going to do that here. A little dashed line to kind of separate the parts of the matrix that represent the left-hand side and the part that represents the right-hand side. Drawing that line like that is optional. All right, and I think that I usually won't do it, but that was just a little discussion about why it's called an augmented matrix. And if you see a line like that, it's really just a marker to separate left-hand side from right-hand side. But if we know that the right-hand side is always the final column, it's always the last column, then we don't really need a line there. All right, so we're going to do things like add a multiple of a row to another row, multiply a row by a constant, stuff like that. Let's think about what is our goal. Our goal is to get triangular form. How about I write as like a little bit of scratch work up here, like goal, get into triangular form. Let's think about what would that even look like for a matrix. Earlier we were just thinking of equations and we wanted to like get rid of the lower left terms. Well, we're not really going to have empty space in the lower left now. We're going to have zeros there. It's going to be like there's a 0 here, 0 here, 0 here, and then some kind of numbers filling up the rest of it. If we can get it into this form, that would be considered triangular because we would get this sort of thing going on. Either think of it as a triangle or like a staircase. I'm going to put that as a little side note. So I want to get those lower left terms to be zeros. And the most powerful of these row operation steps is probably the first one. Adding a multiple of a row to another can help us get some zeros to show up. So what I'm going to do is, I think, we might have more than one option here, but I think I'm going to add -1 times row 1 to row 2. And I like to write something like that to indicate what step I'm doing. Maybe as we go further, I'll start abbreviating it a little bit. But I'm going to be changing row 2, so I'm just going to copy row 1 for now. I'm going to copy row 3. And, all right, what happens? We do -1 times 1. We add it to 1. That gives us a 0 here. That's what I was trying to do. That 0 is the reason why we were doing this step. But we also, as a side effect, we wind up changing the rest of this row. So we have -1 times -1 is +1 getting added to 2. Gives us 3. -1 times 3 gets added to -2. Gives me -5. -1 times 4 gets added to 10. Gives me 6. Seems good so far. We are one step closer to triangular form. Let's move this up. Feels like maybe this will take 3 steps, but it's hard to tell. It might take more. I think I want to go after this 3 that's all the way in the lower left. And I think the way I want to get rid of that 3 is by using a multiple of the 1 that's above it. So we add a multiple of a row to another. So let's do -3 times row 1. Do you want to abbreviate this instead of writing row 1? How about we call it R1 to R3? How about that? Adding -3 times row 1 to row 3. You can write it that way if you want. Remember, when you do that, you're not actually changing row 1. You're not actually changing row 2 either. But we're definitely changing row 3. So row 3 gets a 0 there. That's why we did that. Let's see what happens to the rest of it. Negative 3 times negative 1 is 3, gets added to negative 1 to give us 2. Negative 3 times 3 is negative 9. That gets added to 5 to get us negative 4. Negative 3 times 4 is negative 12. That gets added to 14 to give us a 2. All right, let's take a quick look at this. I kind of want to get another 0 to show up in this thing. You know what, though? I notice a 2, negative 4, 2. That entire row is multiples of 2. So how about this? How about we multiply row 3 by 1/2? We did that on a previous problem, and it made things a little simpler. Let's do it here, too. So this becomes 0, 1, negative 2, 1. All right, I think I'm going to do this in 2 more steps. Because I'm looking at this and I'm thinking, all right, can I get rid of this 1 here? Like, can I turn this 1 into a 0? I guess I could, like, maybe by using a multiple of the 3 that's above it. So if I did, like, negative 1/3 times row 2. Negative 1/3 times row 2 getting added to row 3. That would turn this into a 0. But then I would have to do, like, a negative 1/3 times negative 5, and I would have fractions, and I don't want to do that. So that would be okay, but I see something that might work a little simpler. I'm going to interchange R2 and R3. Swap these rows. So row 1 stays the same, and row 2 and row 3 trade places. We're allowed to do that at any point in time. We just usually don't use that one that often because a lot of times it doesn't help. But look what happens now. Now the position that I'm trying to get into to turn into a 0, now I don't have to use any fractions. I can do negative 3 times row 2. Gonna add negative 3 times row 2 to row 3. Leave row 1 alone. Leave row 2 alone. All right, what are we doing to row 3? 0 gets added to 0, still a 0. Negative 3 gets added to 3 to give us a 0. Whatever else happens, I know we're in triangular form. Negative 3 times negative 2 is positive 6, getting added to negative 5 to give us 1. And negative 3 times 1 is negative 3, getting added to 6 to give us 3. I'll say this is triangular form. Now remember, each row represents an equation. So maybe we could even think of this that way. I'm going to do this as a little side note. I'm going to say this represents, if you think of it in terms of equations, these are coefficients, right? We converted from equations to an augmented matrix. We could also go the other way around. We could convert from a matrix to an equation. So the first equation here represents 1x1 minus 1x2 plus 3x3 equals 4. The second equation represents 0x1s. There's 0x1, so I'm not even going to write that. 1x2 minus 2x3 equals 1. And 0x1s, 0x2s, 1x3 equals 3. I'm going to put this whole thing in like parentheses as a side note. But yeah, this matrix represents this triangular system. And we can do back substitution, right, to finish this off. So we could either think of it by thinking of the equations, like equation 3, equation 2, equation 1. But we don't even need that. You can just ignore that. You could work on the matrix. You could work with row 3, row 2, and row 1. From row 3, I can see that it's telling me 1x3 equals 3. x3 equals 3. And then from row 2, I can tell that it's saying x2 minus 2 times x3 equals 1. So x2 minus 6 equals 1. So x2 equals 7. And then we work our way up to row 1. X1 minus x2 plus 3x3 equals 4. And then we substitute in the values that we know. So x1 minus 7 plus 9 equals 4. You should wind up getting x1 equals 2. So we have found a solution. Let's write it. Solution 2, 7, 3. I think at this point I'd also like to mention we're focused right now on writing solutions in this way, but there is another way to write the solution. So, or you could write x1 equals 2, x2 equals 7, x3 equals 3. As long as they're all there and it's labeled which is which. And, you know, write them in order. The point I'm trying to make with this is that it needs to be 2, 7, 3, not 3, 7, 2, or some other combination, even though we found the 3 first, and then the 7, and then the 2. Now remember, we could check this. We could check this solution in the original system. You've got your x1, your x2, your x3. Plug them in to the original equations and make sure that all 3 of them are consistent, all 3 of them are true simultaneously. But I'm not going to do that for every problem. So we can move on. There's one more thing I want to show you for this section. We've still got a lot more to talk about in regard to linear systems and solving them, and you'll be seeing, you know, a good amount of practice problems and more of this in the next section. But for now, I do at least want to show you one more. I want to show you an inconsistent system. So we haven't seen that yet. How about this? Do you even remember what that means? We said, I'm going to remind you of something we said earlier. Let's point it out. An inconsistent system. Earlier, when we did these 3 cases, there was case 1, case 2, case 3. We said case 2 is when you have no solutions, we say the system is inconsistent. So I'd like to show you one of these. I think in the next section, you'll see some of case 3. But so far, we've been doing a lot of case 1. So I want to show you an inconsistent system. So I'm kind of spoiling the answer for you. The answer is going to be no solutions. But let's see what a problem like this looks like. Like what's going to happen that's going to tell us that there are no solutions. So suppose you were just told to solve. Let's pretend we don't know the answer. Pretend we want to solve this system of 2 equations with two unknowns. And, we did a system of this size earlier in this section before we talked about matrices and before we talked about Gaussian elimination or row reduction. But we could do this as a matrix. It'd be good practice. So let's make the augmented matrix of the system, which means we write -4, 1, 1, 8, -2, 4. We're just kind of taking the numbers out of the system that we see a negative. We see a -4, we see an 8, and so on. So let's say it's not triangular form, and I want to do row reduction steps to get this into triangular form. I guess the goal in this case, since this is a smaller system, to get this to be a triangular form, all we would have to do is get rid of that 8. If we could turn that 8 into a 0, we'd have a little triangle here. And I think I can do that if I add 2 times row 1 to row 2. You see how I chose that step? I chose that because I could tell that that is going to make this 8 turn into a 0. Let's copy row 1. We're not changing row 1 right now. Two times -4 is -8. -8 gets added to 8. We get a 0. That's what we wanted. But we also have to do this to the other numbers that are in this row. So, okay, let's do it. 2 times 1 is 2. That gets added to the -2 that was here. That becomes a 0. I wasn't necessarily trying to turn this one into a 0, but it happened anyway. 2 times 1 is 2. That gets added to 4 to give us 6. Okay. So technically this is triangular form, and we should be able to use back substitution. But let's look at what does this row tell us? Because back substitution says you should use the bottom row first. So row 2 says this really represents like a 0x1 plus 0x2 equals 6, right? Because these are the numbers. We've got a 0, 0, 6. 0, 0, 6. Well, which means 0 equals 6. That's what we have found here. The left-hand side is 0, the right-hand side is 6. Well, that doesn't seem right. This is actually never true. It's never true that 0 equals 6. This is never true. That got a little messy there, but I'm saying this is never true. And what I mean by that is there is no value of x1 and there is no value of x2 that will ever make this true. So we've hit a dead end and we say no solutions. That is the answer to this. The problem said solve. The answer is there are no solutions. We could say the solution set is the empty set, which you may have seen before as this symbol. So that's another way to say that there are no solutions. The solution set is empty. Okay, so here I am again. So this is going to be the end of this section. I know we covered a lot of definitions and terminology, but we got to see some examples. You know, the important things about this section are knowing what it means to solve a system, knowing the basic ideas behind this idea of Gaussian elimination, which is a process that we use. It's a strategy that we use, and we're going to see more of it. So if it seems weird at first, you'll get to do some practice in the upcoming sections as well. All right, so yeah, thanks everyone for watching, and I'll see you next time. Feel free to let me know if you have any questions.